So this whole chapter or unit is logic, and we are in section. I don't know what section it is, but section 4 maybe, whatever. We talked about the different aspects of logic. We started from statements, and then compounded statements, and the two symbols, different operations, involved in compounded statements, and that those two symbols, one is called the universal quantifier, and the other is called existential quantifier. They're actually in open sentences in this section. This sentence about open sections. So the difference between a statement and the open statement is that you can always determine the truth value of a statement, whether it's true or false. But for open sentence, it involves one or more variables that you cannot tell the truth value. So you have to specify the variables, the values of the variables for an open sentence to become a statement. Then you can have the truth value. And we discussed quite some properties about the open sentences. And since we are talking about open sentences and statements, the relation between them, or relationship between them, then we can understand the meaning of implication in statements based on open sentences using the two quantifiers. Okay, so let's just look at this, this statement. So Px implies Qx. That's an open sentence because we have variable x. But if we add a quantifier, universal quantifier, namely for each of x in a set S, or all of the elements in S, Px implies Qx. So that's a statement now. So then, so when is this statement true, or what it means for this statement to be true? As we know, for any value of x in S, if you specify the value, then we got a statement, conditional statement, and this conditional statement is false only when P is true and Q is false. So in other words, when is it the true? Either P is true or P is false and Q is true. If you take the counter positive of this implication, this is and, when Px is true and Q is false, so this is and. If we take the counter positive, it becomes P is false or Q is true. So when that happens, then the statement is true. All right. So that means, whenever P is true, and the Q must be true. All right. So that's another way to say it. So if we know P is true, then Q has to be true. Then for any given X, element X in S, in the set S, if Px, then Qx. All right. So P is true, then Q is true. And there are different ways to say this statement. Okay. If P, then Q, right? So that means if P is true, then Q is true. We can, say P implies Q, or P only if Q. All right. So if P is true, then Q is true. That means, or Q if P. Okay. So just invert the wording. Okay. Or you can say P is sufficient for Q. So P implies Q. Or Q is necessary for P. So for uh, you know, Q is necessary for P. So that means when P is true, then Q must be true because it's necessary. Or we say when P is true, then Q is true, of course. So there are different wording for the same statement, for this conditional statement. Okay, so that's the conditional statement. For the biconditional statement, P, if and only if Q. Remember, the arrow is two ways between P and Q. If you still remember the compound statement between P and Q by biconditional symbol. We can also use in different wording. We can say P if and only if Q, or P is equivalent to Q. They're the same thing. When P is true, Q must be true. When Q is true, P must be true. Okay, so that's if and only if and the equivalent. All right. Either they are both true or both false, right? So they're equivalent. P is necessary and sufficient for Q, obviously, because the arrow is two ways. So that includes, P is sufficient for Q, but Q also is sufficient for P. So that means P is necessary for Q also. So P is necessary and sufficient for Q. Or P holds exactly when Q holds. They're equivalent. All right. So that's the meaning of implication. We're just use different wording for the same statement. So this last part of the section is some examples between the wording and the symbolic logic. So you can translate statements from English to symbolic logical or vice versa. For example, if we have statement of this, if a real number is not zero, then a square is not zero. All right, so that's a true statement. You can write this statement as for any x in R, x not equal to zero implies x squared not equal to zero, right? So any real number, okay, it's not zero, then, okay, so that implies square is not zero. You can also, translate this symbolic into English. Every non-zero real number has a non-zero square, or a non-zero real number has a non-zero square. All right. So that's pretty straightforward. And the next example is the statement of the square of any rational number is a rational number. That's a true statement also. So again, we're going to use the universal quantifier, just like the previous example, for any x in Q, the rational number set. X squared also belongs Q. So any rational number has square, rational number. And these examples are important because when you do the proof, for example, you're going to use those quantifiers or symbols instead of wording. So when you claim a statement in mathematics, you want to write in mathematical language instead of English. So the next example is another statement. There is a rational solution of the equation x squared plus 2x plus 1 equals 0. That's also true. The solution is -1 actually. But if we want to translate this sentence into mathematical symbols, we can use the existential quantifier. So there exists some x in Q such that x squared plus 2x plus equal to 1. So that automatically take case of there is a rational number and a rational number at the same time. So whenever there's a wording of there is, it means there exists. So we have to use the existential quantifier. And another example is to translate the statement of every real solution of the equation x cubed minus x equals 0 is rational. Okay. That's also a true statement. In symbolic logic, you would write every real solution. So you're going to use the universal quantifier. So for any x in R, so real, right? Every real, okay? And the solution of the equation, so we write the equation x cubed minus x equals 0. It has to be, x has to be rational. So implies x belongs to Q, right? So every real solution of this equation it implies it has to be rational, right? And the next example is to translate the symbolic logic to a English sentence. So we have the universal quantifier any x in R for any real number x squared equal to 2 implies x not in Q, not a rational number. So it essentially means the real solution of this equation is not a rational number. Or you can say every real number whose square is 2 is not rational. Or given an arbitrary number x, if x equal to 2, then x is not rational. Same meaning. Okay. The next example says the statement, a real number x has a real square root if it is positive. That's also true. If x is positive, then it has a real square root, basically. Reading in symbolic logic, you can write, any real number, so a real number x. Okay, so a real number, so that's any x in R. X is positive implies x has a real square root, right? If it is positive, so you can put the x is positive in the front to implies that x has square real square root, right? Okay. Or you can use everything in symbol without wording if you change the whole thing as for any x in R, parentheses, x greater than 0 means x is positive, implies x has a real square root. You can, so that x has it means there exists. So there exists y in R, a real square root. So translate square root means y squared has to be x. So that's the square root of x, right? So you can write in this way. So that's the last problem is a real square root is the square root of x and it's real. Okay. The last example for this section, I believe, is to translate a sentence into symbolic logic. So it says every even integer greater than 3 can be written as the sum of two primes. That's the Goldbach conjecture has not been proved. Okay, so that's a statement. It's either true or false. We don't know whether it's true or false, but we know it is either true or false. So how do you write this sentence into symbolic logic? Okay, first, we need to define the prime numbers. Okay, so or we can define the set P as the prime numbers in natural numbers. So then we can write the sentence into simple logic as okay, so we have several things. We have even integer. Okay, so it has to be integer and it has to be greater than 3. And then a sum of two primes. Okay, so we need the expression to write this relation. And every even integer, so that implies us to use the universal quantifier. So for any x in z, every integer, and then not just integer, but even. So x has to be even greater than 3. Okay, even greater than, so and, so it has to be greater than 3. So that's and, x greater than 3. So, and then, okay, so can be reading as, so that's the conclusion. So this is a condition here implies that this x can be reading as a sum of two primes, y and z. So there exists y in P and z in P, or there exists z in P such that x is a sum of y plus z. So they exist, so such y and z, or they exist. Okay, but we can write this same statement in a little different way, a shorter way. If we define E be the set of even integers, okay. So we have P as the set of primes in natural numbers, and the E as set of even integers, and then we can write a short notation without any word in here. So instead of writing any x in z, we can write any x in e. Okay, so that takes care of every even integer. And then we can, use the other things the same. X is greater than 3 implies, there are two primes, y and z, such that x equal to y plus c. X can be expressed as sum of these two primes. Or you can even make it a little shorter if you define another set f as the set of even integers greater than 3. Okay, so that takes care of everything in the condition, and then you can write, for any x in f, so every even integer greater than 3. All right, there exists y in P and this z in P such that x equal to y plus z. And in this way, you even don't need to write the implication symbol, the arrow. This can be easily understood. For any x in f, there exists y in P and this z in P such that x equal to y plus c. So this it automatically tells, before the existential quantifier it automatically indicates this is the implication in here. All right. So that's the end of this section. Any questions for this section 4, open sentences?
No, I don't have any questions.
Okay. Let's see. Let me just see the next. Two and three. Okay. So I guess we might start this section a little bit. And the next section is multiple quantifiers and negating sentences. So this is the case when we have more than one variables in open sentence. Then you need to multiple quantifiers to specify every variable in the open sentence to make it a statement. Okay. So in this case, we want to know how to understand the quantifiers interacting to each other and analyze the truth value of the statement, okay, in multiple quantifiers. And one of the things is the order of the quantifiers are important. When you have multiple quantifiers, it matters which comes first. Okay, the first example is open sentence P with two variables, x and y. So this is the first part, 5a. Statements with multiple quantifiers. So in this open sentence P, it's just the relation, x greater than y. That's the open sentence. And x and y are both real numbers. So so here we use two universal quantifiers both of them, but we use universal. I mean, not two, but both the universal and the existential quantifiers in the statement. Okay, so we use X for the universal quantifier and Y for the existential quantifier, so that specify the two variables, so it becomes a statement. So it means for any real number X, there exists a real number Y such that X greater than Y. So that's a true statement. Okay. Right. Well, I guess you just pick up any number X, and then you can easily find the number Y that less than X, for example, X minus 1, yeah, or X minus 2, X minus 3, and so on. So that's true statement. But if you change the order of this quantifiers, then what happens is it becomes totally different. Okay, so the next example, just put these two quantifiers in the reversed order. Okay, so we put the existential quantifier for Y first, and the universal quantifier X second. So then we write this statement. Okay. It says there is a real number Y for any real number X. We have X greater than Y. Okay. So for any real number X, there is a number Y. Okay. Well, I should say it more carefully. Okay. So it says there exists a number Y such that for any X greater than Y. So there's a number, that is less than any real number X. That's what it means in this statement, right? And that is obviously true. You cannot find a number that is less than any real number. Okay, so you know, there are infinite many real numbers. So you cannot find a number Y that's less than all the real numbers. Okay. So in other words, if Y is a real number, then Y is, well, minus 1 is not larger than Y. Okay. Hence, there does not exist a real number Y for which every real number is greater than Y. Okay, so that's another way to say it. You cannot find a number that's less than all real numbers. Okay, so if that number is Y, and then you can find a counterexample Y minus 1, which is less than Y, right? So that's a false statement. Okay. So this is the warning, that talking about this. Okay, so existentially quantified variables are always allowed to depend on any previously quantified variables. All right. Okay, so that's the existential quantifier. For example, for instance, in the first example, we are allowed to choose value y in terms of x, as we did by taking y equals x minus 1, since the variable x was quantified before y. Okay, right? So in the first example, um, you know, x is quantified before y, so then we can choose y in terms of x. The existential quantifier comes second, all right? However, a variable can never depend on another variable that is quantified later, okay? For instance, in example 5.2, the second example, we cannot define y in terms of x since x is quantified later than y, okay? So in the second example, you know, the universal quantifier for x comes second. So if the existential quantifier for y comes first, so y cannot depend on the x value. Okay. So that's the why. That's the reason why the second example is false, right? So we cannot define y in terms of x. All right. So this y is not dependent on x. All right. So it has to be true for all x, in other words. Okay, so that's the first a few sentence about this section. I guess I'm going to stop here and continue next time. Since we only have a few minutes, 2 minutes left, we cannot do too much at this point. But I do want to say one thing about the homework. Did you check the uh, announcements in both courses?
Yeah, I saw the assignments. When do you think you want them in? Do you want them like Wednesday or Friday or like Monday?
I can have it by next week. Anytime next week will be fine. So
Okay.
yeah, I just gave the second exam assignment for this course and the first assignment for the other course, and I want both to be turned in by by next week, sometime next week, because the midterm period is coming in next week, and I have to have some grades for midterm grades um, in early in the week after next. So that's why I need them to be turned in by next week so that I can have some grades.
Okay, no problem.
Yeah, there are not many problems for this two, as you see. I just give it two more problems in this course and the four problems in that course. So since these are both are pure math courses, so we don't have to have a lot of quizzes or tests or whatever. So I'm not considering to give you guys another separate midterm exam. I think we just use the quizzes to give you a to midterm grade. And by the end of the semester, we're gonna have a few more homework, obviously, and by the end of the semester, we're gonna have a final exam. So That's what I'm thinking. Uh, that's the only the exam we have. Uh, so just make sure you know